Right, so as promised, I am going to go back to term one's work and do videos for the lessons that we did then. So the first one of them, I'm going to do chemical equilibrium. So this is going to be quite a long video because I'm going to go through all of the notes. You can fast forward and rewind and pause as you like. Okay, so I'm going to start at the beginning. I'm going to go through the notes as if I was teaching you. So we started off looking at what the difference is between a closed system and an open system and an isolated system. So remember, an open system, you can have a change of substance, so things can come in and out. So for example, if you look here, this is open. So if there was a reaction happening here, gases could escape if there were gases made. Temperature can be affected here. The thing can, whatever's in there can cool down or heat up if you're adding heat. A closed container, you can see here we really just put a lid on here. So if gases were produced, they won't be able to escape. But we can change the temperature still by adding a flame or by putting it in a cold water bath or a ice. And so it can interact, but nothing comes in or out. An isolated system, nothing comes in and out, and this is a cutaway of this. This is like a thermal insulator. So this is where it will just, like I said, it's a cutout. So imagine this whole thing would have been closed, and that stops even temperature from being changed. All right, so just bear that in mind. Okay, so a reversible reaction can obviously only happen within a closed system, can happen in an isolated system, but we know from equilibrium stuff that temperature can be affected. So we're working with closed systems in equilibrium. Okay, so what is a reversible reaction? Well, now we know that Haber process. I've worked with Haber with you since grade 10, and we know nitrogen gas plus hydrogen gas gives you ammonia gas. But now I'm telling you that the reverse is true. Okay, so not only can the nitrogen and hydrogen make ammonia, but the ammonia can break down into nitrogen and hydrogen again. So if this is in a closed system, it will go back and forth, back and forth, back and forth until it reaches what's called a dynamic equilibrium. Okay, so this is where if we put nitrogen and hydrogen in a container, for example, and we allow it to react, this reaction will start to happen quite quickly, and it will have a high reaction rate. Now remember, everything that affects the reaction rate that we've learned before will affect this rate. So we increase the temperature, we can add a catalyst, we can do whatever, and whatever you add to it or do to it, it's going to increase the number of products. Okay, but now because it's reversible, my ammonias can start breaking down and create nitrogen and hydrogen, and so we've got a high rate going forward, low rate going in reverse. But the reverse reaction is speeding up because you're getting more and more ammonias, and the forward reaction is slowing down because you are getting less and less nitrogen and hydrogen. And so at one stage, the rate of that forward reaction is equal to the rate of the reverse reaction, and that is when it's in equilibrium, not when products are equal numbers. No. Only when the rate of the forward reaction, so how quickly the forward reaction is happening, must equal the rate of the reverse reaction, how quickly the reverse reaction is happening. When they're equal, it looks like this is finished. Okay, it looks like there's no more left over. So a dynamic equilibrium refers to a reversible reaction. So it has to have a reversible reaction. You can't do an equilibrium question with a non-reversible reaction. It also has to be in a closed system. If you have an open system and you've got gases and the gases are escaping, there's no way that you can then go back to reactants. The forward reaction and the reverse reactions are taking place at the same rate at equilibrium, and hence the concentrations of reactants and products are constant. Notice it doesn't say are the same, they say they are constant. So if you have, so this one took the number of particles as the ratios. So you can see 2 ammonias, there's 3 hydrogens and 1 nitrogen molecule. So you can see they're not equal, but they're in equilibrium because their reaction rates are equal. All right, so we're going to look at graphs in this section. So your graph type 1, there are 2 types of graphs that we need to pay attention to. The first one we're going to look at is a reaction rate. Please always take a look at what is on your y-axis when you're going to analyze graphs. The rate of the reaction rate versus time. Okay, so these are like your normal reaction rate graphs that we did in reaction rates in grade 11. But what's happening now is that you're now getting 2 graphs on one Cartesian plane. And you will only get 2 graphs with this type of graph, this type of graph. So it's reaction rate. You need one for the forward reaction. And now you'll see here, my reaction rate starts off quite high because if we only have reactants in a container, they will start reacting quite quickly. But we can see that the reaction rate decreases. Okay, and it decreases. We know that this is the gradient. Oh, sorry, it's not the gradient. Okay, this is an actual plotted line of reaction rate, but you can see it decreasing as it moves along time. Okay, so this is not looking at the gradient of this graph. This is just looking at how your reaction rate decreases. And at some point, it levels off, which means your reaction rate lands up in the same place. Okay, there's your reaction rate, and it becomes constant over time. Now, if we take a look at our reverse reaction, so this is our dotted line. I'm not going to bother with dotted line. And what happens here is we start off with a 0 reaction rate. Why? Remember, this is 0 because in the beginning we didn't have products, and so as the first products were made, as the reactants reacted, so the rate of the reverse reaction increased. And at some point, they must land up on the same line. And we can extrapolate this back to show, let me try and get it right here, to show that both of them here will have a reaction rate of whatever this reading would be. They will both have that reaction rate, and that shows that both of them have the same reaction rate or rate of reaction, and so they are now in an equilibrium. Okay, the rates can change depending on what you do to the equilibrium, and we're going to talk about that later. Okay, so here we have another reaction. This is ammonia with hydrogen chloride making ammonium chloride. So the reaction has stopped, but both the forward and the reverse reactions are continuing at the same rate. So here we have the 2 reactants, there we have the products, and now we've got a container that contains products and reactants. So that is what's going to happen. Remember, you can't see the reactions happening. This is a microscopic level. It's not even a microscopic level. It's an atomic level. Okay, we can't actually see what's the reactions happening, but we know that there's a little bit of both reactants and products in here. Okay, so that is what it looks like to have equilibrium. So the next graphs we are going to look at are the graphs where we're taking a look at the concentrations or the actual number of particles here. Okay, now I've done this 2 ways, and you can get it like this, or you can get it with each individual reactant getting and I actually prefer it when each reactant and each product has their own line. But here we have number of particles. Okay, so we're looking at this particular graph looks at both the reactants and both the products. Well, in this case, one product. And this is called a homogeneous equilibrium because they are all in the same phase. They're all gases. Okay, so it's not that important to know that. So if we take a look here, these are number of particles. So we can see that we start off with a high number of reactants, because if we place nitrogen and hydrogen in an empty container, closed empty container, we will have nitrogen and hydrogen. And as they react, they start to decrease. Okay, Here, my products, I've started with 0. Remember, this is always your origin. So this is 0. And slowly, the number of particles start to increase of our product. Now, take a look. They don't have to land up on the same line. In fact, this one, I'm going to draw it in pencil, one of them actually could surpass the other one, and you could land up with that one going above it. It's okay. They're each going to have their own amount of particles based on their ratios. Okay, so here we can see, the number of particles started leveling off here. And here, the number of reactants started leveling off here. So we know this is in equilibrium because the number of particles are now constant of reactants and products. So we know that products are still making reactants and reactants are still making products, but it's not changing the number of particles of each, because as the forward reaction happens, the reverse reaction happens. Okay, so I hope you understand that. Okay, now concentration. Now this is a very similar graph. That's why this is type 2, because we're looking at number of particles or concentration. Remember, concentration is number of moles per volume. This is number of particles. It could also be number of moles. So here we're looking at a volume that is constant, and we're checking the concentration. Now, if our volume changes, our concentration will also change, because remember, it's number of particles over volume. So if your volume increases, okay, that means that the number under your fraction is going to get bigger. That makes your whole fraction smaller. Okay, the whole thing gets smaller. If your volume gets smaller, so you are decreasing the size of the container, and your number of products stays the same, your whole concentration will increase. Now, this is quite important when you're thinking of acids and bases and equilibrium. So remember that when we are changing concentrations, we are actually changing the volumes. Okay, and it depends on what you're doing to the volumes. We're keeping the number of moles the same. Okay, so here, for example, we have now, oh gosh, the colors are not gone funny. It's actually been labeled, so it's actually fine. So we have one graph that looks like that. Now, it shows this. Technically, this graph is incorrect. Okay, it's not done to scale at all. So the graph is kind of correct in that it's doing what it's supposed to do, but the scale is actually wrong. I'll show you what it should look like. In fact, maybe I should just delete it and show you. I think we did do this in class when we did it. I'm going to show you this now. Okay, so let's do it like that. You can redraw it if you want to, or you can just keep it the way we're doing it here. Okay, so what we're going to do is, I'm just going to do it in pencil so that I can get it right. Okay, so I'm going to say, all right, I know that I have nitrogen and hydrogen. I can actually start it anywhere. Okay, I can say, what happens if I did just had the same number of particles? And I'm now going to look at nitrogen. Okay, so I know nitrogen's concentration is going to decrease. How do I know nitrogen's concentration is going to decrease? I actually want to do it a bit longer than that. I know it's going to decrease because it's a reactant, and so it decreases. Now, what I want you to see is that ratio over there. Okay, I'll talk about it now. Now, let's say I had the same number, the same concentration of hydrogen. Okay, so I'm going to start with the same concentration of hydrogen. But the thing is that for every one nitrogen, 3 nitrogens react. And so this is going to go down 3 times as much, because 3 times reacted. So there will be 1, 2, 3, and there is my 3 to 1 ratio. So this dropped 1 ratio, this dropped 3 ratios because that's a 1 to 3. Okay, now let's take a look. In the beginning, we started with 0. I feel like I'm starting the Bible here. In the beginning. Okay, so in the beginning, initially, let me say that. Initially, nitrogen was not there, so we start off at 0. But we know that the concentration is going to increase. But now if we think about it, here's another ratio. So it goes up by 2 ratios. 2 is made. Well, for every 1 nitrogen, 2 is going to be made. We start at 0. So if we go up here, we're going to land up crossing this. And there is our ammonia. So here I'm going to make that purple. And there is the purple one. Okay. Let's go here because it went down 3 parts. That's our hydrogen because it was a 3 ratio, and because this one reacted 1 part, I'm going to do it like that. So this is now a kind of two scale graph of showing there's 4 parts. Okay, they're equal parts. And we know that the first one is going to decrease by 1 part because 1 reacts. The second reactant is going to decrease by 3 parts. So from there, 1, 2, 3, and there it lands up over there. And then number 2, the product is going to increase by 2 parts. So we go up 1, 2, and that is what's going to happen over here. Okay, so this is a much more accurate graph, and I hope you can draw it and make sure you see what you're doing. Okay, so here again, let's take a look here. So here we have another concentration versus time. Now this is a lot more accurate because I didn't even put the unit over here. This is, you must make sure you have a unit on that. Oh, my dog is barking now at me. Okay, so concentrations. Here we can see we're starting with 0 over here. Here these two are starting further up. So we know these are the reactants. This is the product. When they land up going so that their concentrations become constant, in other words, a horizontal line or a, what's the word, a 0 gradient, then we know they're in equilibrium. Sorry, I just need to pause this for a little while so I can see what my dogs are doing. Okay, so the concentration remains constant, therefore the equilibrium reached. Okay, so now this is graph 1. Why? Because it's the rate of the reaction. And now you can see here we have 3 graphs here. Sorry, we have 3 graphs. We have one for each reactant and one for the product. If we had more than one product, you would also put a graph for the product. As many products as you have and as many reactants as you have. Sorry, I'm shouting at my dogs now. Okay, so here we have a forward reaction. So this is where our hydrogen and our iodine, okay, I'm back. Sorry, my dogs. Okay, so we have a forward reaction. And we know that the reaction rate is going to decrease. Here we have the reverse reaction. So they take in the HI and they go in making hydrogen and iodine again. Please note that even though we can see this has become the reactant and these have become the products, we still refer to them as the original equation, that these are reactants, and that is the product. Okay, so we always look at the forward reaction when referring to reactants and products, otherwise it's going to get so confusing. So always go with your forward reaction. If hydrogen and iodine are reactants, they are reactants. HI is product, they are products throughout the whole thing. Okay, so it just makes it easier. And now you can see whether the reaction rate has whether 2 reaction rates have become equal. This is now in equilibrium. Okay, once equilibrium is reached, there are 3 external factors which can change the equilibrium position of a particular reaction. So now it's in equilibrium, but if we add something, take away something, increase or decrease the pressure, increase or decrease the temperature, something will happen. Okay, so that's what happens now. Okay, so the application of equilibrium. So the first thing we're going to look at is Le Chatelier's principle. So Le Chatelier says when an external stress or a change in pressure, temperature, or concentration is applied to a system. Now remember, pressure and concentration are kind of the same thing, because I just spoke to you now about if you're decreasing the volume, you're going to increase the concentration. But if you decrease the volume, you're also going to increase the pressure. So we often talk about pressure with gases and concentration with aqueous solutions. Okay, so just bear that in mind. So if there's an external stress, so it can be a change of pressure, change of temperature, or a change of concentration, is applied to a system. Okay, you must say system, because you're applying it to the product and the reactants in dynamic equilibrium, chemical equilibrium. Okay, so that means that it's in a closed container. The equilibrium point will change in such a way as to counteract the stress. So you change the pressure, the reaction is going to react in such a way as to undo what you've just done. Okay, so for example, if the concentration of a reactant is increased, okay, how do we do this? By adding more of a particle. Okay, the equilibrium will change in such a way as to reduce that concentration again by favoring a reaction. So either the forward or the reverse reaction will be favored. Okay, so when you're answering these types of questions, because you're going to have to explain them, I want you to think of this in order, and you can do it in step form. Please don't give me paragraphs, and they don't like paragraphs either. So answering questions in change of equilibrium changes. Stress. Identify what happened. There was an increase in concentration. There was a decrease in concentration. There was an increase in temperature, whatever. What happened? How did the reaction respond? Which reaction was favored to undo what you've just done? Okay? The reason. Why would it do this? Well, it would want, if you increase the concentration of a certain substance, it would want to decrease that again. And then what happened to the yields? Now the yields is the amount of substances that you have. So your reactants might have increased number of particles. Your concentrations might have increased or decreased of other substances. The temperature increased or decreased, and so on. Okay, so what was the effect? Now, let's take a look at each individual one and discuss how each individual reaction is going to be a factor is going to affect an equilibrium. Okay, so here I have ammonia and water, and we get an ammonium, and this is actually a hydrolysis of ammonia. This is an acid-base reaction. You will know this now because we've done acids and bases, but it's actually an equilibrium. So we have hydronium ions and your hydroxide ions. So if more ammonia is added, so that means we're going to have an increase of ammonia. The equilibrium, now often you can see in textbooks and that they can say the equilibrium will shift to the right. So it's going to want to do that. We say the equilibrium shifts to the right. I prefer to say the forward reaction will be favored. Okay. So why? So the stress is ammonia increased. Okay, the response, forward reaction favored. Reason, because we want to decrease the amount of ammonia again. Well, how is that going to happen? Because the forward reaction uses up ammonia. Okay, so the forward reaction is going to be favored. What's going to happen? Well, ammonium and hydroxide ions are going to increase. Okay, water is going to decrease because it's reacting with the excess ammonia, and it's going to do this until it reaches a new equilibrium. It doesn't go back to its old equilibrium, it gets a new equilibrium. Now we also talk about the common ion effect. If a substance is added which contains an ion, which is also in the reaction, in the equilibrium will shift to cancel out the disturbance. So, for example, here we said if we added NH4Cl, now we know that we can break that up. We know this in aqueous becomes ammonium and chloride. Now, if you look at the reaction, there's no chloride. So chloride's not going to do anything here. It's like a spectator ion. But we do see that by adding ammonium chloride, we're going to increase our ammonium ions. So what's going to happen? We need to decrease the number of ammonium ions. And the way we're going to do that is by shifting to the left, shifting the equilibrium to the left. Be careful your wording here. Or we're going to favor the reverse reaction. Okay, I prefer that explanation. Why? So that we can decrease the number of ammonium ions again, and that's going to cause an increase in water, an increase in ammonia, and a decrease in hydroxide. Okay, so there it is there. So let's take a look at another example. So this is, if we're going to increase or decrease concentration, we're going to look at how it affects the graphs. So here it's the Haber process again. It's the most useful reaction because it has really nice ratios and it's just it's so easy to use. So what's going to happen is that, imagine they were already in equilibrium. There we can see, okay, they reached equilibrium. Then there was the spike. Look at the spike of just one of them. It was an immediate spike. Can you see that? At that time, there was, it didn't happen gradually. It didn't have a gradient. It went quick, instantaneously. So this was, the concentration was increased instantaneously. It took no time at all. And so we can see that nitrogen was added. Okay. Now, if we take a look, nitrogen is added. Okay. So we want to decrease nitrogen again. Okay, to decrease it, it will have to react with hydrogen. And so our forward reaction is favored. Okay, and that means hydrogen is going to decrease. So look here, hydrogen was just sitting there all nice by itself, but now it is being forced to decrease. And it will decrease as if it was starting all over again. So notice a gentle curve. And also, that ammonia is now decreasing. Take note that it doesn't take away all of the nitrogen that was added, but it does decrease it again until it reaches a new equilibrium. So I want you to see here that these two do the same thing. Why? Because they are both reactants. So if the one is increasing, the other one will increase. If the one is decreasing, the other will decrease. Now, if your reactants are decreasing, it makes sense that at that time, your product starts to increase because the forward reaction is favored, making more ammonia, decreasing those two. So there's our decreases until equilibrium, and here is our increase. Okay, now what happens? Okay, this is this graph. They're the same graphs. Okay, but now we're just carrying on. Here's the equilibrium. Notice how you had an equilibrium. Now there's a new equilibrium. Notice that they're not at the same concentrations in their new equilibrium. So now something happens. Now we remove ammonia instantaneously. Why would this be useful in industry? Well, if we take a look here, why would they need ammonia? So industry is making ammonia. Ammonia is used for fertilizers and explosives. So we want to make ammonia. And they can't allow the reaction to keep coming to equilibrium. It needs to keep making ammonia all the time to be cost effective. So here we increased our concentration. So we're increasing our yield of ammonia by increasing our nitrogen or hydrogen. Here we are taking away ammonia. And that is what they do in industry. They keep removing ammonia. So what happens now when we look here? This is being affected, but it's decreasing. We want to make more. And so the forward reaction is again favored because we've taken away ammonia, but we need to make more ammonia. Okay, so there's the instantaneous decrease of ammonia, and it's at this time. Okay, and what happens? Well, because it decreased, it will start to increase again because the forward reaction is favored, which means it's going to make more product. Okay, at the same point, right? Nitrogen and hydrogen were just sitting there, no, not bothering anybody, but because all of a sudden the equilibrium changed, they were not in equilibrium anymore, there wasn't any more ammonia, it started to decrease its concentration as well, because the forward reaction was favored, and so they would be used up in the reaction to make the ammonia. Again, please remember that your reactants will do the same thing and the products will do the same thing if you have more than one. Right, so all reactants will do the same thing, there we go, and all the products will do the same thing. So activity, sulfur dioxide and oxygen in equilibrium with sulfur trioxide. Is the forward or reverse reaction favored when more oxygen is added? So more oxygen added, it's going to want to use up that excess oxygen, and so the forward reaction is favored. Is the forward or reverse reaction favored when sulfur trioxide is removed? Let me do another color. Sulfur trioxide removed. So forward reaction is going to be favored again because you want to make more SO3, and so these two have to react to make more of that. What will happen to the concentration of sulfur trioxide if sulfur dioxide was removed? Okay, so let me get another color. Right, so if we take this and remove it, what's going to happen to this? So if we remove that, the reaction is going to, the reverse reaction is going to be favored because you want to make more SO2, and therefore the concentration of SO3 decreases because you're going to have to use up some of that to make that. Please remember, I know I seem to be giving you a lot of reactions with only one product. Remember, like this one has two products, but it will work for all your products and reactants. Okay, page 4. Oh, this is actually quite a lot of work. Okay, temperature. The effect temperature has on an equilibrium depends on what type of reaction it is. Okay, so if you have an exo or endothermic reaction, obviously that's going to make a difference. Now, the one thing though I want you to remember is that temperature is one of the things that affects reaction rate, okay, of all reactions. Okay, so the concentration does affect reactions in the previous ones, but only of the reaction that it was in. Whereas here, if you increase temperature, it's going to make all of them go faster, but it's going to make one go more faster than the other. So let's see here. Okay, here we have an exothermic reaction. Okay, that you can indicate by saying, okay, this is a hypothetical reaction. A plus B is in equilibrium with C plus D. Okay, we have a delta H less than 0. That shows us it's exothermic. Remember, the forward reaction is exothermic, means the reverse reaction is endothermic. All right, so energy is almost seen as a product. Okay, so if you see it as, let's just think about it. What kind of exothermic reactions do we use? We use candles. Candles is an exothermic reaction. So if you have a candle, you are going to be producing light. Okay, so we are needing, I'm sorry, it's a terrible flame, but anyway, we are needing the light. So we are needing the energy. Okay, it's usually given as heat, but it can also be given as light. Okay, and you can also, we know we light fires to get heat from it. Okay, so the heat, okay, I'm sorry, I was disrupted. Okay, so we see it as, we want heat or energy as a product of the reaction. Okay, so there is it. If you think about just even the sports pads that you click that little thing and it heats up, that's exactly what you're wanting. You want it for that heat, and so heat is a product of that reaction. Okay, so if you think of that in exothermic, it's like a product. Okay, reactants, products, and heat. Endothermic, you can think of it now, obviously C plus D is A and B. We always refer to the reaction in terms of its forward reaction. So that's why I've swapped those two around. Now this is endothermic, and so it's going to need to absorb heat in order to react. This often happens in we get in a reaction and it feels cold. So even those pads that they use in sports, some of them actually go cold, and that's absorbing heat. Okay. Remember, you can't give cold, it can only take away heat. So that's what they're doing. And so heat is seen as a reactant in an endothermic reaction. So if you think of them in that way, it's actually much easier for you, because let's say I increase the heat. Okay, if I increase the heat of an exothermic, I'm increasing this product. I hope you see that, the product. Okay, I'm increasing the product, which means the reverse reaction is going to be favored. If I increase the heat here, I'm increasing the reactant of an endothermic, and so the forward reaction is going to be favored. So let's take a look at our favorite reaction, Haber process. It is exothermic, and we know that this is an exothermic reaction because the forward reaction is exothermic, reverse reaction is endothermic. If the temperature, so let's see here, we know that that means it's going to be plus heat as a product. Okay, you can even write that, it's fine. If the temperature was increased, the reverse reaction is favored. Okay, why? Because we're increasing the heat, but we're making heat. It doesn't want more heat, so it has to use up the heat you've just added, and so the reverse reaction is favored. Okay, so if the temperature is increased, the endothermic reaction is favored because it's going to want to use up the energy. If your temperature is decreased, the exothermic reaction is always favored because it's going to want to increase that heat again. Okay, so here is a table of all these different things, and you can go through this and see if you understand it. So let's take a look at the task here. So methanol is manufactured by the reaction between carbon monoxide and hydrogen at a temperature of 300 degrees. A dynamic equilibrium is presented as follows. Okay, so here's our dynamic equilibrium. Okay, and we get a negative. So we know that if it's a negative, it's exothermic. Okay, so we can say plus heat. That doesn't look like an H, but anyway. How do you know the forward reaction is exothermic? Because we have a negative heat of the reaction. Okay, our heat of reaction, or our change of heat, is a negative. So it means the whole reaction has lost heat during the reaction. Which reaction will be favored? The forward or reverse? Okay, so if we added more hydrogen. So if we added more hydrogen, so we're going to increase hydrogen. So we want to use up the hydrogen because we've got too much now. The forward reaction is favored. Okay, forward reaction favored. Which reaction will be favored, forward or reverse, if we increase the temperature to 400? Okay, so if we increase the temperature, it's like increasing our heat as a product. And so there's already heat being made. And if we increase the heat, it's going to want to decrease the heat again. And so our endothermic reaction is going to be favored, which is the reverse reaction. Okay, so this is the reverse reaction. Don't worry about the Kc value about this. I suppose we can do it because we have done it, so let's just do it. Will the Kc value increase, decrease, or remain the same if the decrease of temperature to 100 degrees? So if we decrease it, the forward reaction is going to be favored. Okay, now if we think about the Kc value, remember the Kc is your product over reactant. Okay, so let's see. The forward reaction is favored. That means that our products increase and our reactants decrease. So we know that in a fraction, if we have a big number on the top, our whole value will increase. Okay, and that decreases as well. So the Kc will increase. Okay, what page next? Whew. Okay, now let's take a look what happens to the graph.